So the general idea with related rates is when you have a situation where every quantity is a function of time and you know some of the rates of change at a particular time, then you can play this game with related rates. So first, find equations that relate those quantities. Sources for these equations, so find an equation, that's easy to say, but how do you know how quantities are related? Usually these equations will come from one of two sources usually. Either some sort of geometry, say volume equations, area formulas, or maybe things like similar triangles is a common source of equations that relates quantities. So geometry is one way to get equations. And also, if you're in the sciences, then some equations will just be known, and we'll see an example of that in a second. So sometimes a scientist will come along and give you an appropriate equation that relates all of the quantities in your situation. But once you have an equation that relates all of those quantities, then you can differentiate both sides with respect to t. When you do this, you do have to be careful about the chain rule, right? Every quantity that you've written down is actually a function of time. So anytime you differentiate something, you're going to have derivatives with respect to time popping out. Once you are done taking your derivative, then you can evaluate at the time of interest. And this usually takes the form of just plugging in the values for your derivatives that you knew ahead of time. You might have to find some of those values using maybe other equations. And once you've evaluated everything except the one rate that you don't know, then you can solve the resulting equation for the rate that you want to find. Let's look at one more typical example of using related rates. So here's a situation. Suppose we have a sealed piston that contains 1 mole of gas. A mole is just a certain amount of gas. It's a certain number of gas molecules. So suppose we have a sealed piston that contains 1 mole of gas at this pressure, 760 torr, and a temperature of 293.15 Kelvin. If we pull the piston so that the enclosed volume increases at this rate, a tenth of a liter per minute, while we also heat the whole thing at 3 Kelvin per minute, how does the pressure change? So what I'm envisioning here is we have some sort of cylindrical piston, right, with some sort of piston rod down the middle that seals the end. So by moving the rod in and out, we can move the right-hand face of this enclosed volume. If we move it to the right, the enclosed volume gets bigger, and if we move it to the left, the enclosed volume gets smaller. So we can adjust the size of this cavity. And we've got 1 mole of gas in that cavity, and I'm assuming that no gas is escaping, so this mole of gas is constant. And we have a certain pressure and a certain temperature. All right, so the quantities involved here, we have the number of moles. Chemists and physicists usually, in this situation, call this N. And this is a constant for us. So this one isn't a function of time, right? This particular quantity is actually a constant. There's the pressure of the gas. Let's call that P. Now we know the pressure at a particular moment in time, but if once we start heating things and moving the piston around, this pressure is going to change. So this really is a function of time. We won't write the of t part, the parentheses, but just keep in mind that it is a function of time. We have the temperature of the gas. Let's call that capital T. It's a little confusing to have a capital T and a little t running around, but that's life. The temperature is a function of time as well. You can tell because it's changing, right? We're heating the whole thing. So again, we won't write the of t part, but just keep in mind that temperature is a function of time. And then I guess the last quantity here is the volume. We have to keep track of the volume because here we have a rate of change of the volume. So that means the volume should show up somehow. And the volume, of course, is going to be a function of time as well. All right. So what we need is some kind of equation that in this situation, and when you have gas enclosed in something, some equation that relates the amount of gas, the gas's pressure, its temperature, and its volume. And there actually is a formula that any physicist or chemist could tell you about. It's called the ideal gas law. And the ideal gas law says that PV equals nRT. Okay, so pressure times volume is number of moles times R times T, and R is a constant that depends on the units that you're using. So for these units, torr, Kelvin, and liters, R is a certain value that we have to just go look up. I have looked up the value for R for these particular units, and it turns out it is 62.36. And the units for this are a little bit crazy, but they are what they have to be to make the ideal gas law formula make sense. So it turns out it's liters torr per degree Kelvin mole are the units for R. But it's a constant, right? R is a constant. So when we ultimately differentiate by T, remember that R is a constant and N is a constant. Okay, so here's our relationship for all of that relates all of these quantities. So now let's differentiate with respect to T. All right, on the left-hand side, we have to do the product rule because P times V, that's a product of two functions of T, little t, time. So the product rule says we get derivative of P with respect to T times volume plus pressure times the derivative of volume with respect to time. On the right-hand side, this little n is a constant. Well, R is a constant as well, so we can move those constant multiples outside the derivative, and that just leaves us with the derivative of temperature with respect to time. All right, now some of these things we know. So going back to the original problem, the volume is increasing at 10 liters per minute. So volume we know. We're heating it at 3 Kelvin per minute, so that's the rate of change of temperature. We know that. And we're asking how does the pressure change? So that's going to be dp dt. So it's okay to have dp dt be an unknown because that's what we're looking for. So that means we somehow have to come up with values for the volume, the pressure, N and R. Well, N and R, those are constants that we know ahead of time. And pressure, we know the pressure. It's right here, 760 torr. So we know the pressure. But we don't know the volume, right? We're going to have to find the volume somehow. But remember, the ideal gas law, we differentiated it, but it's also a true characterization of an enclosed gas even before you differentiate it. So we can use the ideal gas law in its original form. In its original form, we know the pressure, we don't know the volume, we know the number of moles, we know R, and we know the temperature. So we can use the original ideal gas law to find V, and then we can put that into our equation down here. So first let's find V. So the original all of the units are compatible, so I'm going to stop writing the units just to save a little space. The original pressure is 760 torr. The volume is what we don't know, so we'll write V. Number of moles is 1. The gas constant R is 62.36, and the original temperature was 293.15. And now we can just rearrange all of this to find V. So what do we get? 62.36 times 293.15 divided by 760 torr. This gives us 24.05. And this must be in liters since that's the volume unit that we have floating around. So now we know the volume as well. So now we can plug everything into this differentiated form of the ideal gas law. So dp dt, that's what we're looking for, so we'll leave that as unknown. Now what we're doing really is evaluating this equation at this single moment in time. So, really, to be perfectly precise, I should put some evaluation bars in here. I haven't named the time. Let's call it time 0. And then evaluate this volume at time 0, evaluate this pressure, evaluate this rate of change of the volume equals N times R times the rate of change of temperature at time 0. Okay. Now this dp dt, that's the one we're looking for, so we'll leave that as unknown. Volume at this time, that's what we found up here, so 25.05. And again, I won't write the units because they're all compatible. The pressure at time 0, that was this 760 torr. And then dV dt at this time, well, we knew the rate of change of the volume at the beginning. That's 1/10 liter per minute. So times 1/10 equals N, which is 1, times R, which is 62.36, times the rate of change of temperature at this instant in time, and that's right here. And we're heating it, so this temperature is going up. So this rate of change is positive. So 3 degrees Kelvin, so +3. Or times +3, I mean. All right, you can see now that the only thing unknown in this equation is this rate of change that we're looking for. So we can just subtract this stuff to get it to the other side and then divide by 25.05. So dp dt at our moment in time is 62.36 times 3 minus 76 over 25.05. So this is, let's see, 62.36 times 3 minus 76 divided by 25.05. So 4.434. And because this is dp dt, it must be in pressure units per time unit, so that's going to be torr per minute. All right. So in fact, the pressure in this situation is going up. And that wasn't obvious to begin with, because if you think about, so what we were changing in this situation is we were increasing the volume and increasing the temperature. Well, heating something up is going to have the effect, all else being equal, heating something up is going to increase its pressure, heating up a gas. But on the other hand, all else being equal, increasing the volume in which the gas is enclosed decreases the pressure. So at the beginning, it wasn't clear whether the pressure will be going up or down, right? Which is going to win, the heating it up, which will drive the pressure up, or the expanding the volume, which will drive the pressure down. But now we know. In fact, it looks like the pressure is going to be going up at a rate of about 4.4 torr per minute.